This video is to help you through today in class while you have a substitute. And so the first thing I'd like you to do is to take out your notes that you had taken last week when you were working on the idea of molecules, electronegativity, and Lewis structures and molecular structures. Go ahead and pause this video until you have gotten out those notes. So I wanted to recap some of the key ideas for those notes. If you don't have these in your notes now, go ahead and put them in your notes. And if you may have just sort of skimmed through the concepts and want to add more detail, of course, add these to that. And when you were watching the video, you had been presented with the idea that when atoms, each atom has a specific electronegativity, and that means its tendency to gain electrons. So for an atom that has lots of protons, a lot of positive charges, it's easier to gain those negative electrons than an atom that does not have a lot of positive charges or protons. Also, the number of shells makes a difference. If you have lots of shells, that means that that nucleus is sort of insulated from all those negative electron clouds, and so it's harder for those electrons to be attracted to that nucleus because it's more or less covered in electrons, and they have a hard time pulling them in. So electronegativity is the tendency for an atom to gain electrons, and it is purely dependent on where it is, better said, how many shells and how many protons it has. So I'm going to jump ahead to the next slide just to return to this one. And just a reminder, you're going to find that fluorine, the orange box over here, tends to be the most electronegative because, one, it has the least number of shells. That means that the nucleus is as exposed as possible. And yet, with just 2 shells, it still has the most number of protons compared to everything else. So what I would do is, if you haven't done it on your periodic table already, make sure to show a line that shows how electronegativity increases as you go across the periodic table, and it increases as you go up. As you go across, remember, you're getting more and more protons. As you go up the periodic table, you have less and less shells, okay? So those are key things. When you have 2 atoms wanting to bond together that have similar electronegativity, it's sort of that tug of war where it is 2 third graders sort of who are the same size, same weight, same strength, pulling a tug of war, and essentially it's easier to sort of share electrons because one isn't strong enough to tug the electron to the other side. Whereas if you have a large person versus a very small person in that tug of war, it's easier to get the electrons, okay? So atoms that are shared, so that tug of war is more equal, we say form a covalent bond, and that forms a molecule. And then just a reminder, molecules tend to be nonmetals bonded together, whereas ionic compounds are where atoms lose or gain electrons. So just a reminder to keep those in your notes. So when it comes to drawing Lewis structures and molecular structures, remember you want to draw clean dot diagrams, and a single electron is a potential bonding site. And whenever you have 2 electrons bonded with 2 atoms, you're going to create a dash between them. Don't forget to always include your lone pairs. Those are 2 electrons that are just by themselves, not bonded to anything. And when you're drawing Lewis structures or molecular structures, always add hydrogen last, okay? So what I'd like you to do is just refresh your memory. What is the general chemical equation for combustion reactions? Okay, so hopefully you remember that it is some type of fuel that is combining with oxygen to burn and produce carbon dioxide and water. And some of those fuels you may have heard before is methane. Yes, methane gas is a common greenhouse gas. So another fuel is also propane, which is something that you might be using in your barbecue grill, the propane fuel to grill your burgers. So what I'd like you to do is stop the video and create a Lewis structure and a molecular structure for methane and propane. All right, next in the notes, I want to introduce the concept of hydrocarbons. We say that fuels are hydrocarbons, and the reason we call them hydrocarbons is that these fuels are made up of only hydrogen and carbon. And within hydrocarbons, there are many different types of fuels, and one of those fuels is called an alkane. So let me just reiterate what I said. Fuels are hydrocarbons, methane and propane, gasoline, diesel. These are all chemicals that are made up of just hydrogen and carbon. And within that category, you have some that are called alkanes. We're going to use alkanes in our classroom. So for that reason, I want you to memorize the alkane and their chemical formula. So the first column where you see 1C, 2C, 3C, that represents how many carbons it has. So let's take a look at methane. You'll notice by methane it says 1C, and if you look at the chemical formula, it just has nothing, which we assume is 1. Where in ethane we have 2C, and that tells you that there are 2 carbons, and then you notice that there are 6 hydrogens attached to it. So I'm going to give you a moment to sort of look at the pattern that you are starting to see as you move down these alkanes in terms of chemical formula. Are you seeing something that seems to be consistent? Well, if you're noticing that for the hydrogens, it seems to increase by 2 every time you go down, you're absolutely right, whereas the carbon always increases by 1. But that makes it easy if you are listing them by order. But is there a trick to algebraically figure out how many hydrogens you have to carbons? And there actually is. So if you look at the chemical formula and the ratio of C's to H's, whatever number the C is, let's say we give it X as a number, the H's are double that plus 2. So let me give you a couple of examples. Let's go ahead and do heptane. Heptane has 7 carbons, okay? And so our formula says I need to take that 7, times it by 2, and then add 2. So 7 times 2 equals 14, plus 2 equals 16. Let's try another one. How about butane, C4? C4, so we take 4, we times it by 2, that's 8, and then add 2, that's 10. Okay, so you can always determine what the chemical formula is if you use that algebraic expression. Now, in terms of learning your alkanes, you'll notice that probably learning the name of a 5-carbon alkane all the way to a 10-carbon alkane is pretty straightforward, right? 5 is called pentane, sounds like pentagon. Most of us know what that 5 is, usually starts with pent. Same with hexane, sounds like hexagon, heptane, heptagon, octagon, octane, and so forth. It's the first 4 that are always a little challenging because they don't really follow a geometric pattern or the Greek pattern that we're used to. And so there are a couple of expressions that sort of help that process. You can use the term "my eager puppy barks," or you can also just use "my elephant plays basketball." If you use these expressions in order, it kind of helps you determine what the order of the alkanes are. So let's use "my eager puppy barks," okay? So "my" stands for methane, "eager" stands for ethane, "puppy" stands for propane, and bark stands for butane. So if I ask you, what is the chemical formula for propane? you would then sort of chant to yourself, okay, my eager puppy barks. That's the third word, so it must have 3 carbons. And then when I know that I have 3 carbons, I multiply 3 by 2 and add 2, and that gets me C3H8. Okay, so a good part of your class today is actually learning these alkanes because you'll be given a quiz next class period. All right, next piece is how many liters of carbon dioxide did you produce, okay? And so what you're going to be doing is you're going to click this document, and on a separate sheet of paper, you are going to determine how much carbon dioxide you emitted in the last 24 hours. So take your class time, what you have right now, what time it is. Think back to yesterday at that time, and think of all the activities you have done and answer the questions accordingly. So within the last 24 hours, do you normally take a shower? If you do, how long is that shower? You might be taking only a 3-minute shower, in which case for the first part, you would divide that quantity in half. You might be someone who likes to shower a long time, and you're taking a 20-minute shower, in which case you're going to have to multiply this at least by 2.5 times to get the number of carbon dioxide that's released. Once I have you determine how many grams of carbon you have released in the 24-hour periods, I would like you to actually calculate how many liters of carbon dioxide that is. I'm going to go through that calculation a little bit in just a little bit. There are a couple of terms I want to talk about, or ones for your calculations. When it says drink a bottle of water, that drinking a bottle of water means that you are buying a sealed bottle of water from the store, cracking it open for the first time and drinking it. It is not talking about refilling your water bottle, okay? So this is purely purchased water, okay? And I think the rest of them are pretty straightforward. Yes, we have everything in terms of food. If you are eating something that is a meaty sort of meal, it does not have to necessarily be a sandwich or a burrito, but if you're like, yep, that is a meaty meal with meat in it, then consider that a meat sandwich. If you are eating a more cheesy vegetarian, but with like cheese or some dairy product, call that a cheese sandwich. And if you're eating just grains of some sort, that could be a slice of bread, call that a bowl of porridge, okay? So I'll let you sort of adjust what you think is best in your 24-hour period. So next piece is, well, how do you calculate the let me make sure I'm still online. Good, okay. Just wanting to make sure I'm still recording. So how do you actually calculate this? All right, and the way that you're going to do this is that you are going to need to know that 22 liters of gas always equals 1 mole of gas, okay? So that means, stoichiometry, right? That means if you know how many grams of CO2 you have produced, you can convert it into moles, and then from those moles, you can convert it into liters and record that quantity. And that's all I'm going to ask for you to do for your sub-plans, and just keep in mind you will have a quiz on your alkanes next class period. All right, I want to hear only good reports from the sub, and I will see you next class.